Take two.
Okay, this is part 2 of a mini lecture on evidence for evolution. We were talking about different categories of evidence, and in the first part 1 of this lecture, I talked about comparative anatomy, and this is the figure that I was referring to. And you can see that the homologous bones are color-coded to indicate which are similar across each of these organisms. All right, so what I want to do now is to talk about something that Darwin actually couldn't talk too much about, and that is the age of the Earth and the presence of fossils. So at the time I mentioned, remember in Victorian England, most people thought that the Earth was about 4,000 to maybe 6,000 years old. Darwin and other scientists of the time were beginning to suspect that the Earth was much older, but we didn't have there was not a lot of supportive evidence. But since that time, modern analysis has relied upon the use of radioactive isotopes to date rock and fossil remains, and this is called radiometric dating. Radioactive isotopes decay at a known rate. For example, there's one isotope of potassium. It's called potassium-40. It decays at a rate of 1.26 billion years. And the expression, or the way that we talk about the decay, we talk about its half-life. So it's 1.26 billion years. So that means that if we start with, just to give an example, we start with 10 grams. At the end of 1.26 billion years, I'm only going to be left with 5 grams because half of it will have already decayed. And what biologists or geologists have done is they compare the amount of potassium-40 to normal potassium in modern rock, and then look at what we have in rock that's much older. And so geologists now put the age of the Earth at about 4.5 billion years. And that is a number that I want you to memorize. I will ask you about that. All right, so again, Darwin couldn't really talk too much about the age of the Earth. He did talk a little bit about fossil remains that represented organisms that have lived in the past that may or may not be similar to modern day organisms. But at the time there was not that many fossil remains that were known to the scientific community. Today, many more fossils have been unearthed, and so we have a number of different evolutionary stories. The most famous probably is the fossils that depict the evolution of the horse. And we know that the horse The ancestor of the horse began as a sort of a collie-sized animal that had 4 toes in the front, 3 toes in the back. It was what we call a browser, which means that it fed on leaves, not grass. And it had a very short snout, so not much like a horse. These early horses, an old name that you might run across is Eohippus, which means dawn horse, or Hyracotherium. And I'm not going to go into a lot of detail about the evolution of the horse, but I do want to show you the sort of a more modern evolutionary sort of a tree. And this is a representation of what we currently think about the ancestors of the horse. So it's not, as you can see from that, it's not a straight lineage from that dawn horse to the modern horse. That's not how it happens. Apparently there's a lot of dead ends, but ultimately from this small animal we have the gradual appearance of a one-toed animal with very long legs. Essentially it stands on its toes, has a long snout with teeth that have very high crowns, because this animal evolved to feed on grasses, and they're very hard, very tough. They wear down teeth fairly rapidly, so they have very tall teeth. And their behavior is also, as we mentioned I think earlier, in line with that evolutionary type of scenario. This is, as I mentioned, one of the earliest stories of evolution. In the textbook that I had you read, there is a little discussion of another organism that has changed over time. And that would be the whales. Okay. Okay, so this is 1613, figure from the reading that I had you do. This is showing you the ancestors of the whales. And this is showing you some of the modern whales. And it's only been recently that scientists have unearthed organisms that show a transition between early ancestors and the organisms that we know today as the whales. And one of the fossils of the early whales is called Ambulocetus. And this is a fossil that's about 49 million years old. And you can see in the figure that this is sort of a transitional fossil that's beginning to lose its ability to maneuver on land very successfully, and it's moving toward the ocean. Remember that the whale is a mammal, so we're looking at an organism that over time left land to move back into a different environment.